All right, good morning, everybody. All right, good to see you all. All right, we lost a few numbers. Maybe they'll show up in a bit. I think was there a party last night? No? It's a pretty quiet town. I didn't see much going on. Anyway, so yeah, I think the first 2 days were good. We tried to kind of articulate how the early chemists and kineticists came upon this field of chemical kinetics, how they identified like important reactions in a system that may contribute to certain experimental phenomena that they're observing. I think the key thing to notice is this is still a field that's less than 100 years old, yeah, and a lot of discoveries continue to be made. One thing I said in the beginning was the purpose of models is not to fit the data, yeah, it's to sharpen the questions. That quote by Samuel Carlin. So you can see that the early kineticists were following the same philosophy, right? You had a reaction, acetaldehyde, being converted to products. You can fit it with an equation, K times CH3CHO to the 3/2. It fits just fine, yeah? And it actually reproduces the experimental data. So why go through all the trouble to figure out what the reaction steps are, and so on? Well, the reason is because it gave them more understanding, right, of the system, gave them more understanding maybe how they can control reactors that would convert acetaldehyde to different products. And it's the same thing today. We can fit any function to an ignition delay time curve. It doesn't have to be a chemical kinetic model. Actually, we don't even need 10,000 reactions and 2,000 species to predict the ignition delay time of N-heptane for a gasoline engine. You could do it with probably 5 equations if you wanted to, right? So why go through all this trouble? Well, our goal is not to just fit the data. If you want to understand the system, maybe design at conditions beyond where you've actually conducted experiments, then you need to have some fundamental understanding of what's happening. And that's what chemical kinetics is all about. These detailed models are trying to get you more and more insight into the reactive system and maybe make some new discoveries. One thing we can know is essentially what they're doing when they find these reaction mechanisms are identifying sometimes even new reactions. And even today, people are finding out new types of reactions that are happening which were not previously conceived of in a reaction mechanism because some experimental data that they have generated or some computational theory that they have conducted identifies that the chemistry, the kinetics, the reactions that are happening cannot be fit with the regular chemistry sets that are available. And therefore, sometimes people add new reactions. Sometimes they are optimizing the mechanism, the thermal data, the transport data, the kinetic data. But one thing you should keep in mind, if you're not, again, going to be in the field of actually developing chemical kinetics, maybe some of you are just taking experiments like ignition experiments or flame experiments or a reactor experiment. You know, I caution you, do not just go and start tweaking the parameters in the model just to fit your data set. And that happens in a lot of papers. Okay, sometimes it gets published. I mean, the kinetics community kind of says it's not a good practice, yeah, because people have taken a lot of effort to build these databases, and they have identified where the errors are. They've assigned thermal data, transport data, kinetic data, with uncertainties, but they generally know what those uncertainties are. And if somebody goes in and just changes one number by a factor of 5, then just to fit their experimental data, it's, that you could say inconsistency gets propagated in the literature, and later on, you know, it becomes very hard to then deconvolute what are the actual errors. So today what we're going to do is we're going to start actually looking at how we generate this data, thermal data, yeah, transport data, and kinetic data. And my goal today is, you have a lot of the slides. I'm not going to go through every single slide, okay? Because, again, the slides are there for people who actually want to build these models in great detail. And some of you might want to do that. You can refer to the slides. We can be in touch after. But my goal today is to show you what tools are generally used by the community, and what are the uncertainties around those tools, what are the errors, and then if you're using kinetic models or you want to make modifications, you understand how they've generated this data, and what the sources of errors are, sources of uncertainty, how they can even be improved. And that's kind of what we're going to go through today and probably the first half of tomorrow morning. So we'll start with thermal data. So every kinetic model needs 3 types of data. We say thermal, transport, and kinetics, right? So, and kinetic data. And thermal we already talked about. It's a heat of formation, the entropy of formation, the heat capacity of molecules as a function of temperature. This is required for every single molecule or every single species in your reaction mechanism. Stable species, radicals, ions if you have them, and so on. Kinetic data is your Arrhenius rate constants. Well, you first have to write your reaction equation. Ethane plus hydrogen goes to form ethyl plus H2. You write your reaction, and then you assign some Arrhenius parameters, A, N, EA, and so on. And then you need, and then these 2 actually are enough. Most papers you'll see, people only publish the kinetic data and the thermal data because that's all you need if you want to simulate something like a batch reactor, a homogeneous batch reactor where there's no gradients in temperature, no gradients in, spatial gradients in temperature or mixture fraction. Similarly, stirred reactors, flow reactors, you don't need any of these. And many of the papers, you find people are just publishing the thermal and kinetics. Only the groups that actually look into flames have gradients in temperature and pressure, gradients in temperature and mixture fraction as a function of space. So we'll talk about that. They need the transport data for all the species in the mechanism. And sometimes it's a problem. Many people are doing flame experiments, and they want to validate, or they want to compare their experiments against numerical data, and they can't find a model in the literature that has any transport data. So I've worked in this area, so I'll show you some of the tools we can use to get transport data and approximate it and how to put that in a kinetic model. So we'll go pretty quickly. I'm not going to talk about all the equations, because equations are equations. You can look at them and plug in the numbers when you want. I'm going to show you more of the tools and the applications of the tools and where the uncertainties may lie when you generate this data. So let's start first with thermal data. So you know thermal already. Thermal is important because it's needed to determine if a reaction is exothermic or endothermic based on the heat of reaction. The CP value will be used to determine the heat capacity of the gas, which determines the temperature, right, and the pressure of the system. Then you need to also be able to calculate the Gibbs free energy of reaction, because the Gibbs free energy is used again for the equilibrium constant and the reverse rate, if you prescribe the forward rate. Now there's 3 different ways the community typically calculates thermal data. Well, 4. One is experiments, but experiments are very difficult. So most of it done today now using a computational technique. So we'll talk about the first one, group additivity method. Lately, our group at KAUST and others have started replacing group additivity with machine learning because it's much easier and actually better than traditional group additivity to predict thermal. We'll talk a bit about that. And then also quantum chemistry calculations. That's using theory to calculate the thermodynamic properties of molecules. So why do we need thermal data? Well, again, if you have something like this, a flame, or this is just a reaction, A going to B reversibly, A is consumed, B is produced. This is the kinetic regime in the beginning, and this is the thermodynamic equilibrium regime in the end. And again, for a simple process in a reactor, thermal data is enough to calculate what's happening at equilibrium. But again, in a reaction mechanism, we said every reaction is an elementary reaction and follows the principles of microscopic reversibility. So we need thermal data for every species, even in a detailed model. So you guys, this is again the basics of thermal data. We covered this already. I just want to show you why it's important also to understand thermal data even in a complex reaction kinetic system. So this is an ignition delay. This is a potential energy surface of different types of reactions that happen when a fuel is oxidized at low temperature. So we said a fuel like N-heptane, with C7 and C7H16. This is your typical diesel fuel surrogate, also a surrogate in gasoline fuels. The first thing that might happen is you abstract a hydrogen from one of the sites and you form a fuel radical. It's depicted here as R, the fuel radical, and this is showing you a typical fuel radical for an alkane, R. And this radical can, at low temperatures below about 900 Kelvin, well, there's two things this can do. It could break by scission, by a beta scission reaction, leading to an alkene and another radical. We'll cover those in great detail. But at low temperatures, these bonds can't break. So typically what you have is you have an O2 addition to this site. O2 from the gas phase, oxygen adds to the site, and you form a peroxy radical. That's shown here. There's a series of reactions that happen. We're going to talk all about these reactions in due course, but just for today, let's understand that there's a series of reactions. R goes to RO2, there's an isomerization, there's another O2 addition, and then you get some products being formed. So each of these steps is an elementary reaction. And you can see here, this radical has some energy. If you add oxygen, you form the peroxy, which is a stabilized intermediate. It has to overcome a barrier to isomerize and add oxygen again. And each of these steps is reversible. So the radical can add oxygen to form the peroxy. It can also break back to form the radical and oxygen again. So each step is reversible. And the forward rate is prescribed by Kf, the forward rate constant. And the reverse rate has to come from the thermodynamics, the Gibbs free energy of the reaction. And so if we have the thermal data for N-heptane, so you need the thermal data for this guy, you need the thermal data for oxygen, and then you need the thermal data for the product, which is C7H16, H15, yeah, because this is a radical, H15, O2. So this would actually be this would be for the radical C7H15. So if you have the thermal data for C7H15 plus oxygen goes to form the peroxy C7H15O2, which is a radical. And if you have the forward rate constant, then if you have the thermal data for all these species, you can get the Gibbs free energy of equilibrium. You can calculate the reverse rate constant. And then you can start to see this potential energy surface. The kinetics are very much governed by the Gibbs free energy, because the equilibrium of each single reaction depends on the forward rate, but also on the Gibbs free energy of reaction. And if you don't have the thermal data correct, you're not going to be able to predict the concentrations of all these species very well. And all these types of reactions, they play a role in what we call low temperature ignition. I've seen some posters out there. I don't know if those posters are looking at low temperature ignition or high temperature ignition. But if you're doing low temperature ignition, what happens in a diesel engine, what happens in the N gas of an SI engine during knock, that's usually around like 600 to 900 degrees Kelvin. Then you have all this low temperature chemistry happening. And this is showing an ignition delay curve. And one thing you can note right away, again, and for those of you who are not familiar with these curves, this is the ignition delay time. This is the inverse of temperature. So this is high temperature. And 1 is your marker that it's 1,000 Kelvin, because it's 10 to the 3 over T. So 1 is 1,000 Kelvin. And you can start to see already, at around 950 Kelvin or so, you can see that you form a high temperature ignition curve. At low temperatures, around about here 650 or so 1 over T of 1.4. This is the low temperature ignition points, and then you have intermediate, that's so-called negative temperature coefficient behavior. And predicting this is very complicated. You need all these reaction steps for your fuel. This is for N-pentane. And we see here, if we just take a typical model with some fixed thermal data, you can predict a black line. And what these other curves are showing is if you change the thermal data by just 10%, then the curve changes drastically, yeah? So you don't change the kinetics, you just stay in the thermal data for these different species like RO2, QOH, O2, QOH. You change those thermal data by 10%, and the ignition delta curve changes by a factor of 10. So it's a big difference. So you need to get the thermal data right to predict these things accurately. Another thing you can notice, at the high temperature, it made no difference. So that tells you at high temperature, if you change the thermal data of these low temperature related species, it has no effect, because the high temperature kinetics is governed by different phenomena. So even if these thermal data for some species changes, then it doesn't matter much. So I think around 2000, there was a paper in the Proceedings of the Combustion Institute where they revisited the thermal data of a very simple molecule, OH radical. Yeah, and actually every model before 2000 had the wrong thermal data for the OH radical, the most important, well, the two most important radicals in any kinetic system are H and OH, yeah? And then there was a paper by, who was it? It was Warnatz, Jürgen Warnatz, very famous kineticist who passed away maybe about 8-9 years ago. He wrote a paper in the symposium about revisiting the thermal for OH radical. Very simple molecule. No one thought we need to check the thermal again. He checked it around 99, wrote the paper in 2000, and showed that the thermal data was off by about 20%. And if you changed it, of course, everything changes in the high temperature region because it's very much dependent on our main reaction, right? H plus O2 goes to O plus OH. And if you change the thermal data of this guy, the equilibrium changes and everything changes. So nowadays we have the right thermal data for most of the small molecules in the mechanism. But still the big molecules, like N-heptane, all these peroxies, the thermal data has to be approximated. And that's what we're going to talk about, how to approximate this data. Okay, we covered this already. Tabulated data, enthalpy of formation, we've looked at where it comes from, the entropy. So how do we determine these values? Well, you could do these experimentally, right? Well, there's something called a bomb calorimeter or a combustion calorimeter. This was used in the 50s, the 60s, the 70s to get thermodynamic data, specifically the heat of combustion. And from the heat of combustion, you can get the heat of formation then of species participating in that reaction. Now, this is fine for a very limited number of species. You could do this for N-heptane, a fuel molecule. But what happens for a radical? You cannot put a radical species inside of a calorimeter and measure the heat of formation. It's not possible, you can't. And many intermediates like aldehydes, ketones, unstable enols, you can't even buy them and synthesize them and put them inside the experiment. So these experiments were good in the sense that they laid the foundations of how we determine these things, but even in the 50s, scientists started to think about what can we do to predict thermal data for all these complex reaction mechanisms that were coming about. And so they left experiments. Experiments are too expensive, they're time consuming. You can't do the experiment for most of the species in these very complex radical-driven chain reaction mechanisms. So the non-experimental methods then are, okay, ab initio quantum chemistry. Here we solve the Schrodinger equation for molecules, and from that you can, together with solving the stationary point energy, together with statistical thermodynamics, you can calculate entropy, heat capacity, enthalpy of formation at different temperatures. Of course, we cannot really solve Schrodinger's equation for anything other than the hydrogen atom. So I'm not going to go into the details of quantum chemistry in these lectures, but quantum chemistry, we can just say everything we do today is an approximation of the Schrodinger's equation. We'll show some of those approximations later on today. But ab initio still has errors, uncertainties, because for any molecule, other than hydrogen atom, we're always making some approximations of the electronic structure. Nevertheless, the theories that are applied today, those modified formulations are very accurate. You know, we're typically within something like half a kilocalorie or away from actual values, so known values. And we'll talk about, you know, more about that afterwards. So, but ab initio, yeah, it's one method. That's going to be the last one today we talk about. First, we'll start with group additivity. It's the simplest way. If you want to generate thermal data for hundreds of species or thousands of species, you're going to go to group additivity because it's the most fast and effective in terms of computational cost. Okay, so let's talk about this group additivity. This was pioneered by scientist Sidney Benson. Benson was a chemist, and in the 40s and 50s, he started to see all these reaction mechanisms being developed for complex kinetic schemes. And he said, we need thermal data. And he started to think about what is a simple way to approximate the thermal data, the thermodynamic functions for a molecule. And he pioneered a method called group additivity, which said that the thermodynamic function is dependent on the nature of the structure of the molecule. So he already knew the electronic structure, the structure of the molecule should determine the enthalpy of formation, the entropy of formation, the heat capacity. And at those days, he could not calculate the actual bond energies from first principles. So he started to say, from observations, can we assign some values to specific groups that are inside of a molecule? So depending on the atom and what this atom is connected to, that's what determines the nature of the molecule and its energy. So he says the nature of each atom, the nature of the bonding partners, as well as some long-range effects of how this group or this atom is situated in the rest of a molecule, can be used to predict the thermodynamic data. So he split any molecule into groups, and then he said each group contributes to the thermodynamics, overall thermodynamic function of the molecule. So let's consider a very simple molecule, yeah? Ethane is shown here, C2H6. This is a symmetric molecule, okay? And if you look at this, there's essentially two groups. There's basically two of these CH3 groups connected together. Very straightforward, right? So he says in this molecule, you can simplify it into two identical groups. And it was known from experiments already at the time in the bomb calorimeter that the heat of formation of ethane is 84 kilojoules per mole. And again, this is in the NIST database. You can look at this. In those days, in the 50s, he simply looked it up from experiments. And then he said, okay, ethane has 84 kilojoules per mole. Sorry, minus 84 kilojoules per mole heat of formation. Therefore, each group, each CH3 group is minus 42 kilojoules per mole. And then similarly, the heat capacity had been measured at 52.49. Therefore, the contribution of each group is 26.25. And similarly, the entropy is given, has been measured, and then the contribution of each group. It's not just the groups, we'll see. There's other things we need to consider, like the symmetry of the molecule and so on. But he started to develop this kind of understanding. Then he said, you take something like propane. Now, propane has two CH3 groups again, but then it has another group in the middle. Okay, it has a carbon that's bonded to two carbons and two hydrogens. This guy is bonded to two carbons and two hydrogens. This one is a group that's a carbon bonded to one carbon and three hydrogens. And like this, so again, you just simply then measure the heat of formation of propane. Because the CH3 groups are already known, right, from ethane. They're already given at 42. Then the only unknown group here to get to the total is the middle group, and then he assigns some value for the middle group. So it's a very, like a linear addition of groups in the molecule. Very straightforward. Now, for entropy, it wasn't so straightforward because you got to consider things like the symmetry. So you have to make some corrections when you want to calculate the symmetry of the molecule and the optical isomers that are present, because symmetry is something, entropy is about disorder in the molecule, right? And in order to understand or to know how disordered the molecule is, you need to know, are there molecular symmetries that exist within the molecule due to rotations, or external symmetry based on the structure, or if there's optical isomers that are present. And again, if you're a chemist, you care about all this in great detail. If you're an engineer, you look for simple rules to figure these things out. So these corrections are quite simple. Okay, the entropy, the change in entropy is a function of minus R ln the symmetry number of the molecule. The symmetry number is a product of the external symmetry and the internal symmetry, and these are due to the external symmetry is due to the number of external rotations that are possible. Internal symmetry is the number of internal rotations around bonds. So if we look at ethane, ethane is a symmetric molecule. If it rotates on whole axis, its external symmetry is 2. And our rule of thumb is every methyl group in a molecule is a rotor, and it can rotate. And every time it rotates, it contributes to a symmetry number of, internal symmetry of 3. So ethane has 2 methyl groups, so 3 times 3 is 9. And then you get 9 times 2 is 18, so the total correction here is minus R ln 18. You can get similar corrections for the number of optical isomers. You have to add plus R times ln of the number of optical isomers. Okay, optical isomers, a bit more challenging to figure out. Ideally, you would have to draw this in a code, or say in the software, and take a mirror image and see if there's an optical isomer. But a simple rule of thumb we can say as an engineer, if you have a carbon atom or a central atom that's bonded to 4 different other atoms, then it has 1 optical isomer. So you see here a carbon bonded to a hydrogen, a fluorine, a bromine, a chlorine. If you take a mirror image of this, it looks the same. Yeah, so you have an optical isomer. And this optical isomer is non-superimposable mirror image. And again, these can be atoms that it's bonded to or groups. So a carbon that's bonded to 4 different groups gives us an optical isomer. Or a carbon bonded to an OH group, or a carbon bonded to an OO group. And again, these are simple rules of thumbs you can use if you want to build your thermal data in a kinetic model. And then, so this would give us everything we need for determining all the thermal data that you need for a molecule like ethane. Okay, you need the groups to get the heat of formation and the entropy, and then you need the groups again for the entropy, but then also some corrections for symmetry and optical isomers. Now, what about radicals? Well, radical, again, is simply a parent molecule like ethane, but you take away a hydrogen. So if you take away the hydrogen here, you get the radical, right? So to calculate now the heat of formation, the entropy of formation, the heat capacity of a radical, you simply document based on the bond dissociation energy of the bond that's broken. So again, the change in heat of formation will be changed based on the heat of formation of the parent species, as well as the bond dissociation energy, the bond that's being broken. And then that now means for any parent molecule, you can calculate the thermal data using group additivity. And then for the corresponding radicals, you simply take that parent and remove the atom that you want. It's typically a hydrogen. Sometimes it could be an oxygen or an OH group, and so on. And then these are the typical bond strengths, bond dissociation energies for different types of bonds, right? So for a primary group, you would subtract 101 kcal. For a secondary hydrogen in the middle of a molecule, you subtract 98.45 kcal. And for a tertiary, moving a hydrogen from the middle, 96.5, and so on. So then you can do this for allylic radicals when you have double bonds and you abstract the hydrogen from away from the double bond, then you subtract 88.2. So again, these tables are all available. This is for an alcohol. This is for an aldehyde. Again, all of these things change your bond dissociation energies for determining the thermal data for the radical species. So this technique can now be applied to anything. You can apply this to alkanes, alkenes, alkynes, alcohols, ethers, aldehydes, ketones, pretty much everything. All you need is some parametrization that's already been done against experiments or against quantum chemical calculations. And nowadays, I'll show you later on, this is what we have some softwares that are available in the community that have already tabulated all these groups. And then all your job is to go there and say, these are the groups in my molecule. This is the symmetry numbers. These are the optical isomers. If it's a radical, it's a radical. It'll provide you the thermal data. But keep in mind, it's all based on the user prescribing the right groups. So if you make a mistake, that mistake is going to be there in your answer. And so it requires some good chemical intuition to calculate these properties well. And then, okay, you can have different types of groups depending on the nature of the bonds that are there. So even Sidney Benson, in his book, documented different types of carbon atoms. So carbon bonded to single bonded carbon atoms, carbon with a double bond, so carbon-carbon double bonds, carbon-carbon triple bonds, allylic bonds where you have two dienes together, two carbon atoms bonded together by double bonds, aromatic rings, so CB was for aromatic rings, fused aromatic rings like PAHs, and so on and so on. Alcohols, carbonyl groups, nitrogen inside of a molecule. All of these things can be identified as groups. And then you get simply a table like you see here, the group's contribution to the heat of formation, the group's contribution to the entropy, and the group's contribution to the heat capacity at different temperatures. And when Benson made his book, this is a very nice book, Thermochemical Kinetics, he documented these tables. Now we have these tables inside of a code. Okay, so let's look at one example for a complex molecule. You have isooctane, yeah, 2,2,4 trimethyl pentane. So it's a pretty complicated molecule. Yeah, it's C8H18 and many different types of groups. So first, what you do, you go to the molecule and you look. Okay, what are all the different groups that are there? Well, first, you can see you have a bunch of methyl groups, CH3 groups. We have 5 of those in the blue. So C, a carbon, which is bonded to a carbon and bonded to 3 hydrogens. That's called a methyl group. We have 5 of those groups. So we write down 5 groups of methyl. We also have, in the green, we have a group that's a carbon, which is bonded to 3 other carbons and 1 hydrogen. So that's a tertiary group. We have 1 tertiary carbon group. We have also then in the red, 1 carbon, which is bonded to another carbon and another carbon, so bonded to 2 carbons and 2 hydrogens. So that's a secondary group. And then finally, we have another group, a carbon, which is bonded to 4 other carbons. So in total, we have 8 groups, 4 different types of groups, but a total of 8 groups in whole. So that's enough to calculate the heat capacity of the molecule and the enthalpy. Just these groups, we go back to the table here. We look up the contribution of these different values. So this is a carbon bonded to a carbon and 3 hydrogens. This is carbon bonded to 2 carbons and 2 hydrogens. So all these, this is the primary, the secondary, the tertiary, the quaternary. These are four groups. These are the contributions. We simply add them up, and we have the heat of formation. Now, entropy is harder, right? We need to know the symmetry. So there's no external symmetry for isooctane because, again, you have a butyl group here, an isopropyl group here. The molecule is not externally symmetric. However, we have a lot of internal symmetry. Remember, I said each methyl group contributes 3 to the internal symmetry. So here we have 3 times 3 is 9, is 27, is 81, it's 273, and then what? Well, now that's 5 groups, 1, 2, 3, 4, 5. So 3 to the 5, but still I'm missing one more internal symmetry because this tert-butyl rotor can rotate and adds another 3 to the total symmetry. So there's actually 6 internal symmetry points, and therefore we get an internal symmetry of 729. And then you have to correct R ln 729 is minus 13.1. Again, this is, you can't, someone might miss the last symmetry of the tert-butyl group. Is it a big deal? Well, instead of ln of 729, you'll take 273. You'll have some error, but it's not a huge error, okay? So people make these mistakes sometimes, yeah, again, that's why the groups that do this well, they know their chemistry very well when they look at these molecules. Okay. And then there's things that are more complicated in group additivity, because it's what Benson found is if you have this molecule, it's not like you just add up the groups and it's enough, because it works fine when you have like a linear molecule like ethane, propane, butane, hexane. But once you start having branches, those branches start coming close to each other. Like the carbons in the coming off the side, they start interacting with each other, and those interactions affect the energy of the molecule. So it wasn't as easy, he cannot just add up the groups anymore. He had to find that there's some intermolecular interactions that are affecting the energy of the molecule. For example, in alcohols, in anything with oxygen, you guys have heard of things like hydrogen bonding. So hydrogen bonding is when you have hydrogen and oxygen within a molecule. They kind of stabilize the molecule. They want to come together, and they change the energetics of the molecule. So it wasn't so straightforward. So we have to do some other tricks whenever we have branched molecules. There's something we call interactions, gauche interactions. A gauche interaction is whenever you have interactions between carbon-carbon atoms within a molecule. And how do you figure this out? If there's a gauche interaction, you got to draw these kinds of chicken feet diagrams. That's what Westbrook always called them, chicken feet diagrams. The actual name is called a Newman projection. So a Newman projection is you imagine yourself standing inside of this bond number 1, and you're standing there and you're looking out towards this bond. So you're standing here in the middle and you're looking out, and imagine what you see. So you're standing here in the middle and you're looking out. If you look out, you're looking at the solid lines, and behind you are these dashed lines, okay? So I'm looking down this bond. I imagine myself, I'm looking away. What do I see? I'll see 2 methyl groups, because there's a methyl group here and a methyl group here. And I'll see a hydrogen, because this carbon is also bonded to a hydrogen. So that's a methyl, and a hydrogen. And then if I turn around and look behind me, I will see a tert-butyl group, this big group here. And I'll see 2 hydrogens, because there's 2 hydrogens bonded to this carbon here. So, and then you look at this, and based on this Newman projection, you see, are there any interactions between methyl groups or carbon-carbon atoms? So right here, we'll see there's this tert-butyl group will have an interaction with this methyl group. What's the molecules, what it will want to do is it wants to avoid these interactions, because every time there's an interaction, it destabilizes the molecule, so it'll try to rotate. So you rotate this bond by 120 degrees, and you move the tert-butyl group here. But you still find there's an interaction between this tert-butyl and this methyl. And you rotate again, and you see that the tert-butyl could also be between 2 methyl groups. Now, this configuration will be unfavorable, because there'll be a maximum number of interactions here. The tert-butyl will interact with 2 methyl groups. So you're always going to get one of these 2 situations. The molecule will want to move to the most simplest conformation, the lowest energetic conformation, which is one of these 2. And either of these 2, we still have 1 interaction. So there'll always be an interaction between a methyl group, in this case, and a tert-butyl group. Here, a methyl group and a tert-butyl. So we say 1 gauche interaction for that along this bond. Similarly, we have to do the same thing on the other bond. Stand on the bond here, look outwards and look behind you. If you do that, you get these different Newman projections. So I stand in the middle here. Behind me, I see an isopropyl group and a hydrogen. And in front of me, I see 3 methyl groups. And then same thing. I see there's there's 2 interactions here. Isopropyl interacts with 2 methyls. If I rotate, isopropyl still interacts with 2 methyls. If I rotate it again, the interaction is always there. So you can't escape it. And for this bond, there will always be 2 gauche interactions. So then in total, we have these 3 gauche interactions, and each gauche interaction contributes about 0.7 to 0.8 kilocalories per mole to the heat of formation. And that's another correction we have to make. And now you start to see it. What appeared to be very simple, group additivity, becomes rather complicated. And then you got to do this for every molecule in your mechanism. If you have 1,000 new species, it's time-consuming and painful. Yeah. But hopefully rewarding at the end, okay? And then at the end, you have something called also 1,5 interaction. This is when a carbon bond has an interaction with a carbon that's 5 carbon atoms away. So this is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So 5 carbon ring can have some type of stabilizing interaction. So based on this 1,5 interaction, you have to add another 1.5 kilocalories per mole. And in the end, your table looks like this for isooctane. So carbon, we have the primary groups, the secondary groups, the tertiary groups, the quaternary groups. The 3 gauche interactions is 0.7 for each one. So times 3 is a total of 2.1 kilocalories per mole. Then the 1,5 interaction, another 1.5 kilocalories per mole. Then the symmetry number. And then you get your total thermal data here. Now let's say I missed the gauche and the 1,5. I'd probably be off now. Instead of 53, I would have 40. I'd have, I guess, 56 or something, 57. So you'd be off by about 3 kilocalories per mole. Well, that's a pretty big deal. 3 kilocalories per mole. 1 kilocalorie per mole at 1,000 Kelvin is a factor of 2 on your rate constant. So we said that just a ballpark, you know. 1 kilocalorie mole on the heat of formation changes your Gibbs free energy at 1,000 K. That makes about a factor of 2 in the reverse rate constant. So that's a factor of 2 is a pretty big number. So this here, if you're off by 3, your reverse rate constant for anything involving isooctane will be off by at least a factor of 3 or 4. Or more, I'd say, factor of 6. So that's why you got to be careful with these things. Now, some people get lazy, okay, and you see some mechanisms. They don't want to deal with all this stuff, so they have something like ice. This is the hydrogen abstraction from isooctane. Isooctane is IC8H18, a simple notation you might see in a model. You take a hydrogen off, you make it IC8H17 plus hydrogen. But you'll find some models, they always write this only in one direction. Yeah? And then they write another reaction like this. Okay? Then they write the reverse reaction explicitly. And then, so you have the forward reaction. And what is this reaction? Well, it's just the reverse of the first reaction. So and then they prescribe A, N, EA for the forward reaction, and you prescribe A, N, EA for the reverse reaction. So you get 2 different kinetic parameters for K forward, K backward. Then your thermal data doesn't matter anymore. All the thermal data is used for is maybe to calculate the temperature of the system based on the heat capacity. And there you don't need very accurate data. The heat of reaction doesn't matter anymore. Well, it will matter a bit for the exothermicity, but again, a few kilocalories here and there is nothing when we're talking about a combustion system, when we're just trying to get the temperature in the end. So you'll see this. Yeah, sometimes people do it like this. Sometimes people write a reaction and they write rev under it, and then they prescribe A and EA. So that basically means they're telling the code, forget about the thermal data, just calculate the reverse rate constant based on these Arrhenius parameters that I give you. Okay, now that's kind of cheating, yeah. But you do that when you have no clue what your thermal data is, and you just tell the code, okay, don't use the thermal, because otherwise you can get, like I showed, very wacky results. If you calculate the ignition delay time and your thermal is off by 10% or 15%, your ignition delay time can change by a factor of 4 or more. So then, so this is the hack, yeah? They just prescribe the reverse rate constant. Now, again, it's not right because, again, we know if it's an elementary reaction, it has to follow the law of microscopic reversibility. And if the reaction has the right kinetic parameters in one direction, the thermal data, if it's done correctly, should give you the reverse rate accurately. You shouldn't have to prescribe it like you see in some mechanisms. Okay, so what can you do? You can do all this in a code, like Therm is a good code. I think it was Professor Bazzelli in New Jersey, I think Rutgers, another university in New Jersey, not Princeton. But he made a code in the 90s, which pretty much many people use today. If you're doing kinetics to calculate, it's basically a group additivity code. You put in all the groups for your molecule, and it gives you the thermal. Pretty straightforward, yeah? The NIST webbook is a database that you can use to identify different groups. This is a code from France called Thurgas from Nancy group. Similar thing. Cranium uses different groups, Joback groups, but essentially the same thing. A bit easier is you can use RMG. Anybody heard of RMG? It's a code out of MIT called Reaction Mechanism Generator by Professor Bill Green. Professor Green at MIT. I think the website is very easy. It's like rmg.mit.edu or something. And that's a good code because it's like thermal for dummies. You just put in the molecule you want, and it gives you the answer coming out. Okay, and because he kind of, they wrote some scripts to say, okay, you have this molecules, you can calculate then the groups, you can calculate the optical isomers. It sometimes makes some mistakes too. Yeah, sometimes it misses some interactions like Gaussian interactions, 1,5 interactions. But again, if you don't know anything and you don't want to deal at all with any of this, you can use RMG. It's a good one. Or I'll show you, you can even use machine learning approach. It's even easier than RMG. Okay, so these programs like Therm, they're just databases of groups and databases of different interactions. You put these into the code. It gives you the thermal data. It tells you how the thermal data was calculated. And then it simply fits the thermal data with your NASA polynomials. And then you get your NASA polynomials at the end. And there's some other codes, like you can also use this to calculate kinetic data. Like if you want to get the reverse rate based on the forward rate, then they have an add-on called Therm Reaction, which will give you the reverse rates for your different reactions based on all this thermal that's calculated and the kinetics that you provide. Okay, well, I had to do all this stuff when I was a postdoc at Livermore, like 13, 14 years ago, like calculating thermal data for so many species, and it was really hard, and I hate chemistry, and I'm an engineer, and so I got fed up with it. So then, when machine learning became very easy and all my students got interested in it, and I said, hey, this group additivity is such a pain. Let's just replace it all. It's all a fitting function anyways. Just replace it all with a machine learning model. And so this is what we have today. And I'm trying to get the community to say, let's just use a simple machine learning model. You provide the input. The input is some structure representation of your molecule. You train a model, a machine learning model, on how those structures relate to specific outputs, which are your thermodynamic properties. And then whenever you have a new molecule, you put it into your machine learning model and you predict your thermal data. And these things are not highly nonlinear systems, so you don't need very complex machine learning models, right? We have some nonlinearities, like these interactions, 1-5, gauche, symmetry. But so you don't need very complicated machine learning models. We have shown you can do this like with very simple neural networks and support vector machines. But the basic idea is, in principle, the machine learning model should work, because everything that we're saying happens to the thermodynamic properties is only a function of the molecular structure. And the molecular structure is just some input molecular features which represent different electronic structural characteristics of your molecule. So we take a molecular fingerprint. You can write this as a smile string, as an inchi. You can even upload like a drawing of your molecule. And then from that, you can translate this into a matrix, yeah? So this is basically what we call a bond connectivity matrix, which basically says the orientation. So each row here is a different atom, and then each column is the coordinate, x, y, z coordinate for those atoms. So you can take a molecular structure and translate it into a matrix. That's very straightforward, and everybody knows how to do that. And then from this thing, based on the structure, a mathematical formulation of the structure, you could identify what we call different descriptors. These descriptors there's thousands of descriptors. There's codes available that you can actually just look at these matrices and give you different things like, the distance between bonds, the connectivity indices, correlation indices, VSA or van der Waals, surface area descriptors. Like this, there's so many descriptors based on the structure of a molecule. You take these descriptors, you feed them into a model, machine learning model, and you predict then your thermal data. So we use a code called AlvaDesk, which basically can give you about 5,000 different types of descriptors for molecules. And these descriptors are like things like the number of double bonds, triple bonds, the distance between bonds, everything, much more than group additivity. Group additivity is only based on groups, but molecules are much more than groups. They have many different features, and chemists already know what all these different features are just by looking at the electronic structure of a molecule. So I skip over a few slides. I mean, machine learning is machine learning. You can take the course from Andrew Ng, and you'll know everything about machine learning. So we use different types of machine learning models, neural networks, support vector regression models. Because the data sets we're using are pretty small, like maybe 2,000, 3,000 different species. You don't need like a deep neural network. You're using a simple artificial neural network, but you got to do proper training so you don't overtrain your model. One approach we use is what we call k-fold cross-validation. So you ensure that the weights in your model are not overtrained or overfitted. I'll just skip over a few of these. You can look at this later if you want. It's basically the principles of neural networks and support vector machines. But I want to show you more like why these things are useful. So for simple straight chain species, again, I'm just showing here for different highly branched molecules with double bonds. We compare neural networks with support vector regression models against, the important thing is group additivity, yeah? So that's shown here in the gray. So the two we have benchmark data for all of these from quantum chemistry. And you can see here that, these machine learning models are fairly more accurate than what you can get from group additivity. And again, this is group additivity, which was done by us, where we made sure all the values were actually correct in terms of all the different types of interactions. And you see here, as you go to more highly branched molecules, the group additivity has larger errors, up to even 5 kilocalories per mole or more against benchmark data. And machine learning is always within 1 kilocalorie per mole, 1 to 2. And then if you go to cyclic molecules, it's even harder to do group additivity well. So you see group additivity these hashed marks here, sometimes it even gives you the wrong sign for the data. And so these machine learning models, I think, are going to be the way to do this in the future. And yeah, now we're working on a project with MIT. We're training against 20,000 different molecules that are there in combustion. And hopefully then that's enough. You don't need to even worry about thermal data anymore. You just put in the molecule and then you can get pretty good predictions coming out. But yeah, this was all only in the last few years. When we want to train for 20,000 molecules, it's hard because you need good data. So the actual challenge is not the machine learning approach. It's having the good training data. So how you get the good training data is from quantum chemistry. So you have to launch a lot of quantum chemistry calculations. So the PhD student who did this thought he was doing his PhD on machine learning, but in the end his PhD was about quantum chemistry because he had to launch like 4,000 calculations. Well, anyway, he's still got a job in Argonne doing machine learning. But don't think you can get away, right? If you're doing machine learning, you don't need to know chemistry or know fundamentals as well. Because in the end, you need good training data, and that's what these models, if you provide good training data, I think there are much better ways to fit than using things like group additivity. Let me just, give me another 6 minutes, then we'll just wrap up the thermal stuff, and we can move to transport next. So I skip over this. And then there's a lot of slides about NASA polynomials. I'm not going to tell you how to calculate NASA polynomials. I hate NASA polynomials. And why? Because this is the reason why. Yeah. Because you look at this. Anybody know why they came up with NASA polynomials like this? Anybody? Heard of the story? Like why it looks so nice? And you might have seen these in like text files. Well, honestly, a lot of the stuff we do in combustion is like ancient technology. Yeah. Yeah. I mean, some of you guys, I heard, were still coding in Fortran, right? That should have been dead like 50 years ago. But we're still doing it today, right? And well, this is another one of those legacy things. So, you know, we have these NASA polynomials. It's a fitting coefficient, just a polynomial with, and it could be any function. It doesn't have to be a 7 or 14 coefficient polynomial, but that's what it is, yeah? And that's what we keep using. And why they used it? Well, you know, so the thermal data is just a fitting of, this is the molecule, the elements, carbon, hydrogen, oxygen, the phase, gas, and then the temperature range 300 to 5,000 with an intermediate temperature of 1,400. And then you have these coefficients. And then, you know, you can't even look at it and understand what's happening. But this is what the code uses. And the pain of this is they made it like this. You had to exactly align all of these numbers in specific columns on your text file. Yeah? So the element had to be written between column 1 and 10 of your text file. Between 10 and 20, you can have some other notes like the date and some other stuff. But then at column, I guess, 25, you have to have the first element. Oh, no, sorry. Column 30, you have to have the first element. Then all the elements have to be done. But then by column 50, you have to have the temperature, the first temperature. And by column 75, it's done. And then 80. And then you ask, why 80? Well, this was the size of a punch card. Like, okay, I mean, this is how people, yeah, they had to code computers like in the 70s using punch cards. And the punch card was a certain length, which only allowed 80 characters across. And we're still today stuck with this 80 characters because of the punch card. Yeah, so that drives me crazy because, you know, I delete one space and everything messes up. Yeah. And you have to do this for like 5,000 species, and sometimes you got one space off. It's a pain, but we still deal with this today. So that's why I'm not going to talk about NASA polynomials. I hate them. So good. These are some databases. So this is a slide. If you ever need thermal data, okay, these are good sites. And if the data is not in these sites, then you can try to calculate it. Okay, we'll stop there, and then let's take a break, and we'll finish up with this after.